In this video, we're going to be talking about thermodynamic states, and we're going to look at the pressure inside of a nerf gun piston chamber. So to get it started, we'll define what a thermodynamic state is. And they are just moments in time that are described by thermodynamic properties. So these are the same properties that we saw in the first video, so it includes things like pressure, temperature, and volume. Next, we'll define the state postulate, which says that there's a finite number of thermodynamic properties that define a state. Now, definitions that use the same exact words can sometimes be confusing, so we'll take a look at the ideal gas law to better explain what the state postulate actually says. So for the ideal gas law, the state postulate essentially says that if we know some of the thermodynamic properties, like pressure, volume, and maybe temperature, we can calculate the other unknown thermodynamic property, like mass. So let's go ahead and look at our nerf gun example. So this is a nerf gun diagram made by Jared Owen, where he just breaks down how a nerf gun works. It's an awesome video I would recommend checking out if you're interested. So because we're interested in looking at thermodynamic states, we'll go ahead and define two different moments in time. The first one we'll say is the moment in time when this piston, which is this circular part with this shaft, when this piston is all the way right here at the beginning, we'll call this the initial state. And when this piston reaches the end of this little lip right here, when it's right here, we'll call that the final state. And right here, there's a little hole that interacts with this bullet chamber right here that allows compressed air to push the bullet out. Now we can look at the initial state in some more detail. So we can look at the initial pressure, the PI, and because there's this little hole right here, it interacts with the surrounding environment. We'll pretend the nerf gun is just in some room on Earth. So the initial pressure, because the piston is all the way back here, we'll say is just atmospheric pressure, or 101.3 kilopascals. For temperature, because this is also still in a room, we'll just say it's room temperature, so 295.15 Kelvin, which is just taking that 22 degrees room temperature in Celsius and adding that 273.15 to get the temperature in Kelvin. We also know that because there's just air in this room, the ideal gas is going to be air, so we're going to look at the gas-specific constant of air, which we know is 2.287 kilojoules per kilogram Kelvin. Now think about the volume. So the volume is going to be this entire volume right here, everything enclosed in there initially. And we can use the dimensions of the nerf gun to figure this out. But for right now, we'll just put a question mark and we'll calculate that in a second. Lastly, we can look at the mass. So we're actually not sure how much mass is inside of this chamber initially, but because of the state postulate, we can use the ideal gas law to find that mass, or calculate that mass. So we're not really sure what the initial mass is, but we can definitely calculate it. Now we can think about what the final state will kind of look like in comparison to the initial state. So in the final state, this piston has compressed the air, so we're expecting a different volume. So we don't really know what the final pressure is, so we're still unsure about that. The final temperature, we'll assume that the final temperature is actually just room temperature. Now this is definitely not going to really happen in reality because the piston is moving molecules of air. It's causing some friction and heating up that air. But because this is a nerf gun and it's not generating that much heat, we'll just say that this is roughly equal to the initial temperature. Now this is always the same right? And the volume will definitely be different because of this final state, but again, we can use the dimensions of the Nerf gun to kind of estimate that. And for the mass, although it would seem that the mass would actually go through this little pocket, this hole right here, interaction, and move this bullet out, we'll just assume the mass is about the same. And if you watch the demonstration by Jared Owen, it's actually somewhat true. So the piston can go pretty much all the way until here, until the air actually gets pushed out. So piston keeps on compressing air, and then the bullet doesn't actually really move until the piston's about in this area. But for purpose of this video and making our lives a little simpler, we'll just approximate the final mass as the initial mass as well. So as promised, we'll go ahead and look at the dimensions to calculate the volume of that chamber. So the height of the Nerf gun, and this image only includes part of it, but the whole thing is 8.74 inches, and this is just from the lovely website Amazon. And now we'll take a look at the width, which is 12.52 inches. So I just estimated that this width of the piston, so the piston chamber is going to be some sort of cylinder like this. And I'm just drawing it vertically to better imagine, but it's going to have some circular bottom, it's have some height, and the actual piston in here is going to be right here. It's just going to be pushing up and down. But we're going to estimate right here, this length right here, to be about 2.36 inches. And we also have to look at this dimension right here, which I estimated about 0.787 inches. And because our pressure is in units of kilopascals, which is kilonewtons over meter squared, we do need to get these into meters. So to convert this, well, we can just write it here actually. In 1 inch, there's 2.54 centimeters, which gives us, pull out the calculator, so our calculator right here, 0.787 times 2.54, about 2 centimeters. So 2 centimeters is equal to, as well, 0.02 meters. Next, we'll convert that 2.36 inches. So 2.36 times the 2.54 gives us about 6 centimeters. So it's equal to 0.06 meters. And from this little diagram I drew, we know that the volume is going to be equal to that area times the height, the base area times this height right here, which is equal to pi r squared h. And right here we have the dimension of the diameter, but in order to get the radius, we'll divide it by 2, so 0.02 over 2. We'll square all of that times the height of 6 centimeters, or 0.06 meters. And this is also meters right here. So we'll pull out that calculator again, and we can notice already that this right here is just 0.01. So we'll take 0.01 squared times pi times 0.06, which gives us 1.885, and there's 1, 2, 3, 4, 5 decimal places to the left. So 1.885 times 10 to the negative 5, and this is going to be meters cubed. Now that we have the initial volume, we can use the ideal gas law. So we'll pull out the ideal gas law again. So PV is equal to mRT, and we can calculate the mass, that initial mass, by taking the initial pressure times the initial volume over the gas specific constant times the initial temperature, which is going to be equal to the room atmospheric pressure, 101.3 kilopascals, times the initial volume that we just calculated. And we're going to divide by the gas specific constant of air, times the room temperature of 295.15 Kelvin, which gets us to, so we're going to take that atmospheric pressure times the initial volume, and we'll bring the times 10 to the negative 5 at the end. We'll divide by the gas-specific constant of air and the room temperature, and that gives us 2.254 times 10 to the negative 5, and this is going to be in units of kilograms. Awesome. Now we can kind of fill in one of the things that we now know. So this mass now is going to be 2.254 times 10 to the negative 5 kilograms. So all we need is this final pressure. But before we can do that, we do need to specify the final volume. So if we look up here and we just kind of guess what the final volume is going to be, if we have this whole piston chamber and we divide it into 2, so this is about dividing it into 2, then we take this half divided by 2 again, so it's about right there, I would say, and then if we divide it by 2 again, we get that final volume. So the final volume we know is going to be 1/8 of the initial volume. And that's just because this volume right here is about 1/8 of our whole piston chamber. So we can say that our final volume, so VF, is going to be about 1/8 the initial volume. So just taking that initial volume and dividing by 8, so that gets us to 1.885 divided by 8 gets us 0.2356, so 0.2356 times 10 to the negative 5 meters cubed. So now that we know the final volume, we can calculate the final pressure. So the final pressure is going to be equal to the mass times the gas-specific constant of air times temperature over the final volume. So this, we can use the mass that we calculated above, so 2.254 times 10 to the negative 5 kilograms times the gas-specific constant of air times the room temperature, all divided by the final volume that we just calculated. And we notice that these 10 to the negative 5s will cancel out. So these two will cancel out, and we can use the calculator to finish this off. So 2.254 times that 0.287 times the room temperature divided by that 0.2356, so that final volume. We get 810.41. 810.41, and this is pressure, so it's going to be units of pascals, kilopascals. So what this says is that the final pressure, or when the piston has moved all the way into this final position, the pressure inside of this small part of the chamber is going to be 810.41 kilopascals, which is about 8 times that atmospheric pressure. And this is definitely built on an assumption that the temperature is going to be the same in the initial and final state, but this is still a pretty cool result. Thank you for joining me on this video. I'll see you in the next one.